Hello, and welcome to a crucial lesson in building robust software systems. Today, we're diving deep into task states and why mastering them is fundamental for any engineer working with distributed architectures. Whether you're a junior developer optimizing a microservice, a mid-level engineer designing a new pipeline, or a senior architect overseeing large-scale operations, understanding and correctly implementing task states is non-negotiable. By the end of this lesson, you will be able to, first, understand why explicit task states are critical in distributed systems. Second, identify common pitfalls like race conditions and zombie tasks that plague poorly managed states. Third, learn how state machines provide a robust solution for managing task transitions effectively. And finally, explore practical implementation strategies and the immense system design benefits that come with a well-defined state management approach. Let's begin by uncovering why these seemingly simple states matter far more than you might initially think. Imagine a bustling coffee shop, but without any order tracking system. Orders are placed, coffee is brewed, but no one knows what's pending, what's brewing, or what's ready. Chaos, right? Customers are frustrated, baristas are making the wrong drinks, and the manager can't even tell which orders are stuck. This is precisely the kind of chaos that can engulf your distributed systems without clear status tracking. When you're managing thousands of tasks per second across numerous servers, knowing the exact status of each task isn't just helpful, it's mission critical. A single lost task status, where a system forgets what a task is doing or where it spans, can quickly cascade into system-wide confusion, leading to resource wastage, missed deadlines, and ultimately system failure. This isn't just about marking something done. It's about maintaining integrity and predictability at scale. Most engineers initially think task status is straightforward. Just mark it complete when it's done. But in the real world of ultra-scalable distributed systems, it's far messier. First, we face race conditions. What happens when two different servers try to update the same task status simultaneously? Without careful handling, you might mark a failed task as succeeded, or worse, completely lose track of a critical task state, leading to data corruption and inconsistent system behavior. Then there are zombie tasks. These are tasks that start but never finish, perhaps due to a server crash or an unhandled exception. They appear to be running indefinitely, consuming valuable resources and blocking dependent workflows, but are actually stuck in a purgatory state. Finally, consider audit requirements. In production environments, especially for financial or regulated systems, you need forensic-level tracking. If a critical transaction fails, stakeholders demand to know exactly when and why each status change occurred, requiring an immutable, traceable history. This is where a state machine approach becomes your safety net. Instead of allowing arbitrary status updates, a state machine treats status changes as controlled transitions with predefined rules. You explicitly define which status changes are valid. For instance, a task can transition from pending to running, and from running to either succeeded or failed. But it cannot, under any circumstances, jump from succeeded back to running. This prevents impossible or illogical states, making your system predictable and robust, even under extreme stress. This isn't just theoretical. Major companies like Netflix use state machines for critical operations, such as their content encoding pipelines, ensuring a video can't be served until it's fully encoded. Similarly, Stripe applies these patterns to payment processing, ensuring a payment can't go from pending to refunded without first passing through succeeded, preventing financial discrepancies. Implementing this often starts with an enum, like our task status example, combined with validation logic to enforce these transitions. Adopting a state machine approach for task statuses brings profound benefits to your system design. First, it dramatically enhances observability. With clear defined states, you can instantly monitor how many tasks are stuck in a running state, indicating potential zombie tasks, or track the average time tasks spend in each state, identifying bottlenecks. Second, it streamlines debugging. When issues inevitably arise, the state history provides forensic evidence. Instead of guessing why a task failed, you see its complete journey through the state machine, pinpointing the exact transition where things went wrong. Third, it enables targeted performance optimization. State metrics reveal where your system is struggling. If tasks spend too much time in pending, you know you need more worker capacity. If running time is high, it's time to optimize the task's logic. Today, we've covered the criticality of task states, explored common pitfalls, and learned how state machines provide a robust solution. We've also touched on practical implementation through enums and their broad system design benefits. To test your understanding, consider this. How would you design a system to prevent zombie tasks using state machines, ensuring they don't consume resources indefinitely?